Hey, I'm Jordan Crivelli-Decker, and this is my collaborator.
Hey everybody, this is Zane Beckwith.
And today we're going to be talking about our paper published in the Journal of Chemical Theory and Computation titled Machine Learning Guided AQFEP, a fast and efficient absolute free energy perturbation solution for virtual screening. Virtual screening in the context of structure-based drug discovery is sort of a critical tool in, any computational chemist's toolkit. And it's sort of integral to the modern drug discovery process. And the power of virtual screening really comes in from the fact that you can screen in silico thousands, millions, in some cases even billions, of different molecules against a specific protein target with basically just compute. But with a lot of these different virtual screening approaches, the actual accuracy of the methods, essentially measuring how well does a specific small molecule interact with a protein, can vary wildly between the different methods. So sort of one of the gold standard methods is something called relative free energy perturbation, and they're the most accurate at sort of measuring the specific affinity between a small molecule and a protein, but they have a number of constraints, essentially. You need to have sort of a reference ligand. Some ligand that you maybe know very well the structure, the way that that small molecule actually interacts with the protein, or you have some sort of reference affinity value. So if you're starting a drug discovery program, maybe you know the protein target, but you have no chemical matter on a specific target. So this would be, these would be the undruggable targets, as they say. Relative free energy perturbation methods are not going to work. So this is sort of where absolute free energy perturbation comes in. So absolute free energy perturbation does not require a reference ligand. And it also, in theory, has better accuracy for hit ID. But again, it is very, very slow. So it's not really compatible in sort of primary hit finding virtual screening applications. This is sort of where our method, AQFEP, comes in. That was sort of developed by Zane and his collaborators, where we are utilizing active learning as a way to use a surrogate model to help guide which ligands we select to run this calculation on. And then from there, we sort of apply this active learning approach to show that this approach is very effective at screening large virtual libraries quickly and efficiently.
AQFEP is a really interesting project for us in the group because it was one of the first, if not maybe the first project that we embarked on in what's now known as the ALG group. And a lot of that idea and motivation came from our VP of drug discovery, Andrea Bortolato, based on his extensive experience. And so in particular, we really wanted to see if we could find something that would bridge two extremes in between the typical approach for high throughput virtual screening, where you have a scoring function that's very fast, but has pretty poor accuracy and especially pretty poor sort of generalizability outside of whatever particular protein systems it might have been trained on or fit to. That on the one hand, and then on the other hand, very computationally expensive affinity prediction methods. So we wanted to try to find something that could work kind of in between those two extremes, that could work fast enough to be used in a virtual screening campaign, but have something approaching the accuracy and especially sort of the generalizability of a free energy perturbation approach. So AQFEP was our approach to try to find that kind of maybe a sweet spot to basically take free energy perturbation approaches and apply them to a virtual screening scenario. Can we take an absolute free energy perturbation approach to make it so that it can be run against thousands, hundreds of thousands, millions, billions of compounds in a more automated way that takes now on modern GPU hardware an hour or less. And so that unlocks the ability to say, okay, now I can run against larger libraries to try to find hits. So relative free energy is typically about a day or more. Absolute is at least a week. And so that's why it was really exciting when we were able to find a way to say, okay, for our particular use case, we can do an absolute free energy perturbation approach in a matter of an hour or so. Obviously, we're doing shorter simulation here. We're not getting something for free. There are downsides to that. So one of the one of the difficulties with the AQFEP approach is because we're doing drastically less simulation and less sampling of the conformational state of the system, it's really sensitive to the quality of the starting conformation, the starting pose of the protein and the ligand, which is kind of a bug and kind of a feature if you're giving it sort of the wrong pose, a pose that this ligand wouldn't adopt in real life. It's going to give you a significantly worse affinity than that compound might actually have. But I say it's a feature because it was kind of part of the design that you have to be very careful and give it a good starting pose, which is a very difficult problem in itself to get a good pose.
Zane is specifically referring to some of the plots in Figure 3. We're looking at essentially how well do AQFEP affinity values correspond with experimentally derived affinity values between a set of ligands and their affinity measured against a specific protein target. We sort of evaluate how much the input pose actually impacts downstream ranking performance. So on the x-axis in this plot, there's the aligned pose is sort of the most leftmost x position, and that actually refers to if we were to, these are sort of like experimentally solved structures, so we actually know the exact conformation of how the ligand is bound to the protein. If we actually align our input molecule directly to that crystal structure and then score it with AQFEP, we can look to see how accurate in ranking performances that method is against the whole benchmark, and that's measured on the y-axis here. And then as you move along the x-axis, you consider more and more and more poses generated in this case from a docking scoring function. And as you can see, at around 3 or 4 poses, you start to get to the sort of maximum ranking performance that you can get. And that's really great because while the method is definitely sensitive to the input pose, if you can increase the number of poses, score additional poses that you provide to AQFEP, you end up, still being much faster than something like AFEP or RFEP, but you don't sacrifice too much ranking performance. So as Zane mentioned, the AQFEP method is quite fast, and you can run it at a scale that is much greater than sort of standard free energy calculations, but again, it's still not quite fast enough. Even just applying docking, so fast empirical scoring functions that run on CPUs, so can be quite cheaper, sort of in the hundreds of million domain, can take 40,000 core hours, which is substantial. It's not nothing. It's thousands and thousands of dollars. In addition, applying sort of free energy calculations to a library of even 10,000 ligands for sort of like a standard relative free energy calculation is going to take upwards of 80,000 GPU hours, which that is substantial. And again, even on outdated hardware, not even the most up-to-date GPUs that are available now. And AFEP is even slower than relative free energy perturbation and should take somewhere like 4 to 10 times longer. So clearly, if we want to apply these free energy calculations at a scale that's useful for a primary hit finding campaign, we need to sort of think of some way to improve this or optimize the approach for sampling the library. So in these other cases, typically what people will do is they will exhaustively screen every ligand in the library. And again, in these sort of make-on-demand or large libraries, not every ligand is created equal. So one of our collaborators, Rafael Gomez Bambarelli at MIT, sort of mentioned some work from Dave Graff, working with Connor Coley, talking about applying active learning, which I'll talk about in a second, to virtual screening. And so this work was super impactful, and we were heavily inspired by it. And essentially what they do in that work is they sort of treat virtual screening as a Bayesian optimization problem. They initially sample this large chemical library with an initial selection of ligands, and they score all of them with their Oracle method. their scoring function. And then from there, they take that initialization pool of data to train a surrogate model, which roughly approximates this scoring function through, again, a machine learning model, as opposed to actually running a physics-based simulation. In the paper, we sort of tried 3 different approaches. One was just a sort of standard ligand-based machine learning model that is used quite frequently in cheminformatics and machine learning, which is just a random forest with sort of molecular fingerprints which encode the ligand into a binary bit vector. And that approach is super fast, it's pretty accurate, and it's great for scale. But like Zane mentioned, because we can run AQFEP at such a large scale, we actually are able to get enough data to begin to consider whether or not deep learning architectures would be more accurate at predicting these values. And so we also tested 2 different deep learning architectures. One, which is called ChemProp, which is sort of a very well-cited and very effective method, which is a message passing neural network, which attempts to featurize the chemical graph of a ligand to predict some value. And then lastly, work together with a PhD resident in our group named Gary Tom, and he was at the University of Toronto at the time. And this method that we call GraphDoc essentially tries to use all of the data that we generate in these approaches. And so what Gary came up with was sort of this idea of let's featurize the chemical graph, but also include sort of some local neighborhood around the protein. Basically, what we show is that this GraphDoc approach is actually the most performant in these Bayes-opt experiments, and more performant than both the ChemProp method and the random forest method.
So to test the AQFEP approach, specifically in this study, we wanted to look at a retrospective test against a pretty well-known, well-characterized system, the CMET protein, that has quite a bit of experimental data already known on it. So figure 3 in the paper shows some of these retrospective comparisons for the AQFEP approach against some of these baseline methods, and we see quite good accuracy when compared against the experimental affinities. And what's encouraging is we are significantly more performant than the cheaper scoring function-based approaches, either existing docking scoring functions or also cheaper physics-based approaches, things like NMGBSA, for those of you who know the field. We show improved performance over those. But what's also really exciting is we actually are approaching the performance of what is the industry standard for relative free energy perturbation, the Schrodinger's FEP plus tool. We're seeing correlation with experiment that is quite close to the performance that they publish with their tool against this same retrospective target. We also wanted to look at what's called an enrichment study against the same retrospective target, the CMET target. So this, we used a library of only about 1,000 compounds. A library where we have some known hits, things that are actually known to bind and be pharmaceutically relevant for this compound. And what we're trying to do here is see how well can our approach, the AQFP ranking function, find those known active compounds when you're screening against all 1,000 compounds. So figure 4 shows the results from that study. What we're trying to show is whether a method can find the known hits, the known good compounds earlier, can rank those higher in the rank ordering. And so we compare in this plot to a known, well-established open source scoring function, the Bernardo function. And so what you can see here is our approach, the AQFEP ranking, does find the compounds quite early in the ranking. It ranks them very high, whereas the Bernardo approach only finds a couple actives early, and then most of the other actives are only ranked much lower. And so in real world terms, that might mean that somebody actually pursuing a drug discovery campaign would need to buy many more compounds to start screening experimentally to try to find those good actual hits. Whereas using the AQFP approach, it's ranking them much higher, and so you're going to have to buy pure compounds. You're going to find good chemical matter to start from much earlier in your campaign. And so that was really promising to see that, yes, in retrospective, but still somewhat more real life scenario, we were able to see good performance and significant improvement over what was sort of the standard approach.
We also wanted to see how this approach performed on a slightly larger library and against a more challenging to model receptor. And so to do this, we took a library of around 12,000 ligands that are commercially available and screened them against the GLP-1R receptor, which is a GPCR protein that is related to type 2 diabetes. And again, GPCRs are fairly difficult to model with physics-based approaches. If we see that our method is effective in this case, we can sort of expect that our method is going to be effective against other challenging protein targets that share some of the characteristics of this protein. But probably the most simple to understand finding from this paper is thinking about hit rate. And so basically this is a measure of how, if we only screen 10% of our library, how likely is it with our model guided strategy are we going to actually screen the known actives against this protein target? Specifically using the ChemProp method, we're actually able to identify both actives in every iteration. And so that's super promising, showing that this method is able to sort of effectively cut through some of the noise that exists in these large virtual screening libraries, and with a much smaller compute budget, identify known actives. That result was super promising. However, in this case, we knew the answer, and it was still not quite big enough to really reflect what is common in virtual screening workflows. And so to do this, we did a blind prospective test. And in this case, we're not actually able to talk about the protein target. But in this case, what we did was we screened a large commercially available virtual screening library of 1.17 million ligands available from MQL. We applied our best approach from the benchmarking that we performed on the smaller set and applied our model-guided search to screen this library. We performed around 30,000 free energy calculations, which represents a very small fraction of this full 1.17 million. We selected a maximally diverse subset of around 1,424 ligands and sent those for experimental testing. When we got the results of those experiments back, we defined a hit as anything that had an IC50 value of less than or equal to 50 micromolar. And this resulted in 41 diverse compounds reaching that criteria, which results in a primary hit rate of about 2.88%, which is quite good, I think, for sort of undruggable targets where there's no chemical matter around that target, and really like no one's been able to find any ligands that bind to that protein effectively. As we move through iterations of this model-guided search, the AQFEP scores are getting better, in this case lower, across different tranches. And so you can see we had two sort of controls. One was this random bar here, which essentially shows like if you were just to sample randomly from this library, what would be the distribution of AQFEP scores. We also show top dockers in this case. So if you were going to select the top dockers and sample and score those with AQFEP, what would that distribution look like? And in tranches 3, 4, and 5, you can see that through this active learning approach, the AQFEP scores are becoming lower and improving. And this sort of demonstrates that the algorithm is working and is able to find more promising ligands from the perspective of AQFEP scores. And so in summary, we think that this prospective approach, application of this approach, was quite promising and showed very good results for sort of primary virtual screens and a hit finding campaign, and sort of illustrates the power of this method when you apply it to virtual screening contexts.
So something that was really exciting with this publication that we were able to announce is even just that one prospective test that Jordan mentioned against one of our clients' confidential targets involved over 30,000 AQFEP runs, which to our knowledge is the largest free energy run publicly known. But maybe even more importantly is in the intervening time, since we put this together and since we publicly announced it, this tool has really been heavily used by our internal drug discovery team. It's really been a core component of the various drug discovery campaigns that we've been working on. So we're really proud that this was something that we were able to put together that's now had very real impact on really important projects that we're hoping someday will positively impact people's lives by finding new drugs for very difficult diseases. I really appreciate you guys watching this and coming to hear more about our publication of active learning AQFEP. And I'm excited where we're going to be taking these tools and other similar tools in the future. Thank you.
Thank you.